technical difficulty. Okay, so redo that. Can you see it now?
Yeah.
All right, wonderful. Okay, so today I'm going to introduce this open source project. This is on day 4 called V8 RISC-V, and here is the link to GitHub. And this is a joint work with RIOS Lab, which is from the Tsinghua Berkeley Shenzhen Institute, as well as with the PLCT team. Okay. So in fact, when we open source it, we're not the first one to open source V8 engine or RISC-V, we're the second one. So actually Wei's team is the first to do that. And that's an interesting story, and things are developing very fast, and now we're joining force in the same code base. So in today's talk, I'll introduce our journey to develop this new backend. The work is far from complete, and the reason we open source it is because we believe we have established enough of the structure of the project that we can start to invite the community to participate. And today we want to give people a high-level idea of how we go about adding this backend, what's our project roadmap, what is our current status, and in the end, I would give some instructions on people who are interested in participating, how they can get started. And before I go to the details, I want to clarify that, so I'm preparing this talk more with the audience in mind as developers instead of early adopters. So if you are a potential user for V8 on RISC-V, maybe the only thing that you want to look at is the current status, as well as perhaps the project roadmap. But feel free to ask me any questions. All right. Okay, so I assume people know what V8 is. So it's a most popular JS engine. It's used by about 70% of the browsers on the market. And V8 actually is a very mature architecture. In fact, it has gone through many generations of architecture refactoring. And I think it's still doing that, especially on the WSM front. So in this picture, it focuses more on the code generation aspect of V8. Keep in mind that V8 is actually a language VM, so it's not just a static compiler. It has a large component in the runtime, which I didn't cover over here. So in this picture, actually, also keep in mind that for a mature compiler or JIT or language VM, it's pretty well structured. So a good architecture means that you want to minimize the amount of target specific part, which is called the backend, as little as possible, so that you can minimize the effort to add a new backend. So by design, the actual architecture specific part of any language VM is relatively small compared to the entire code base. But here we just zoom in onto the code generation part and highlight some of the components that are part of the code generation architecture. So at the top, let me just get my pointer working here. So at the top, actually just want to give you a few important concepts. So the V8 engine has an interpreter. I will quote it. It's called Ignition Engine. It's not a regular interpreter, but you can consider it as an interpreter for now. And this interpreter is intended for fast startup. The performance may not be as good as fully JIT code, but it's for very short programs, it may not be worth the time to actually compile and optimize it. And to the right-hand side, there is the center of the compilation part of V8, which is called the TurboFun optimizing compiler. And then to the right, there is the WSM, which is a WebAssembly compiler. So in fact, when we talk about V8, we think about JavaScript, but there is also the WebAssembly part. And they are all going through the same code generation structure. Ignition needs a little bit more explanation because unlike other interpreters, which, for example, if you look at C Python, right? So usually the interpreters are written with some bytecode, and then you write C implementations for each bytecode. And what's surprising about this Ignition interpreter, it's actually not called the interpreter, it's called JITless, because even in the ignition mode, still the ignition engine is going through some kind of code generation, which is a very fast template-based code generation. And the benefit of this approach versus the traditional, the C-based implementation for interpreter is that this is very fast. So in fact, for most dynamic languages, if you compare between the interpreter speed and the JIT speed, it's usually 5 or 6 times slow down when you do the interpreter. But Ignition engine, because it still goes through cogen, but the cogen happened sort of ahead of time. A lot of them are happening a lot of ahead of time. So the performance degradation of the Ignition engine, the JITless mode versus the default mode is only 2x. So that's why they are going through this unique architecture. So it's good for the overall performance, but it did add some complexity to the backend. Another aspect of this whole architecture is the built-in functions. So in fact, V8 has thousands of built-in functions. A lot of them are written in JS, some of them are written in C++, and about 60 of them are written in assembly code. So the assembly version called ASM built-ins are also the ones that need to be ported. And built-in functions are very convenient JavaScript features. Some are introduced by V8 themselves. Some are actually part of the JS standard. So these are the top level things that we need to be aware of. And then all of them actually, in the end, all go through the code generator. So in this picture, if you look at the proportion of the picture, I highlighted the part where porting has to happen. So for example, this box here, where there's the instruction selection for the specific architecture, the register allocation, and the most significant component is a code generator. This is where the actual machine code is generated. So this entire box needs to be ported. Also at the top, because the ASM built-in functions are written in kind of assembly code, so they also need to be ported. And finally, V8 has a very interesting mode. So first of all, RISC-V is, I think, the 8th or the 9th backend supported by V8, which is a good thing because that means the architecture is quite mature because they have already supported many different target machines. And so as you can see, x86 is the common one, and ARM, these two are maintained by Google, and then PowerPC, MIPS, and then RISC-V. In fact, for each of these, there is the 64-bit version, 32-bit version. And for all the non-x86 backends, there is this simulator, which is a built-in simulator that allows people to do this special build called the simulated build. I'll explain more on the simulated build. It turns out this simulated build is important booster in terms of the productivity and facilitating the debugging of the generated code. And bear in mind that this simulator is different from, say, QEMU or even Spike, though those are external simulators. So this simulator is built into V8. Actually, we have to also sort of implement the instruction level or functional simulator inside V8, but it turns out to be very convenient for us. Okay, so that's the overall structure of turbofan code generation. And another point I want people to keep in mind is there is actually, for any compiler, there are many levels of IRs. So you can consider them as higher level IRs and gradually lowering down to the lowest level IR, which would be the instructions. And in fact, in the code generation part, I'm going to only focus on the bottom part of the IR, which is conversion from the lowest level of machine independent IR, which is called the machine node IR from the turbofan IR going downwards. In fact, on top of the machine node IR, there are other like JS level IRs and things like that. Those are handled by the platform independent part of TurboFan. So we're not going to talk about those. So to give people, I felt like if I just give PowerPoint slides, people may not have a sense of what the backend is like. So I'm including a few pieces of code here, but there are more pointers in the end. If you are interested in learning more, I have a pretty specific guideline on where you should get started. So in fact, the centerpiece of this backend in terms of the actual porting that needs to be done is at this layer, which is called the macro assembler. So it's under the CodeGen directory. And what is a macro assembler? So macro assembler is definitely platform specific. In fact, anything that is under these target platform directory are target specific, but it's in the middle. So on top of the macro assembler or turbo assembler are what I call the TurboFan machine node IR, which I'll give you an example. Those IR actually are platform independent. And below the turbo assembler are what they call the assembler APIs. So here, let's just look at the centerpiece, and then I'll go up and down to show you how things are connected. So this turbo assembler API, this is a 64-bit add. The naming is a little strange because we inherited from MIPS, but essentially it's add 64-bit. And it takes an register, an operand. An operand can be a register or it can be an immediate value, and the immediate value might be beyond the range of what the immediate field of the underlying instruction would support. So as you can see that it can map to a single add instruction, or it can map to an add I instruction if the immediate field fits into what the instruction supports. Otherwise, you load this immediate value to a scratch register and then add them together. So the semantics is pretty clean, but there are actually tens of these APIs that need to be implemented using the target machine instruction. Some are relatively straightforward, like these ones. Others are more complex. For example, the sequence, the prolog sequence for calling a function or returning from a function and things of that nature. So that's the macro assembler API. So we call it assembler because it's like assembly instruction, but it's kind of, it hides some of the low-level details that typical programmers may not want to worry about when they are coding at this level. So as you can see, these instructions that are lowercase, so the naming convention is capital case is the turbo assembler interface, and the lowercase is the what they call the assembler interface. So these can be found in assembler RISC-V 64.cc. And these naming convention actually are strictly matching the naming convention of RISC-V instructions. So you can see it. This RVLI is a special thing that we're refactoring, but other than this one, everything else, all the instructions that we're supporting and as well as the pseudo assembly instructions are all defined in assembler-RISC-V 64. And these instructions actually are code generator. So when we call add, it actually emits this encoding for add instruction into the instruction buffer. So this sequence is really generating a piece of code that implements a 64-bit add. So this is going downwards to the assembler. And going upward, actually, because add is defined in the macro, so I didn't paste it here. But here, this is actually coming from compiler backend, CodeGen, RISC-V, RISC-V 64. So this code generator is the place where you lower from machine node IR, which is the TurboFan IR, which the IR is very low level. It's almost like C level, but it's architecture independent, except for these ones that start with K-arch. So these actually are done by the instruction selection process, which is one step before the code generator. So here I'm choosing one which implements an opcode that's called truncate double to integer. So this is actually, implementing some semantics that are JS semantics. And __ is a macro that defined to be the turbo assembler. So basically it's invoking this turbo assembler here. There is a turbo assembler function called truncate double to I. It's, again, this implementation is a little long, so I didn't include it over here. But you can see there are perhaps hundreds of these machine node IRs that need to be mapped. Some are very easy, like some arithmetic operations, just one liner can be mapped. Others are more complex. So these are the main places. So these 3 files and the header files are the main places where the target specific things are happening. But there are other places where turbo assembler are used. So for example, built-in, I mentioned that there are ASM built-in functions. So those are all written under this RISC-V 64 directory. And so it's too long for me to paste them, but you can take a look over there. And there it's mainly for implementing a lot of the trampolines and also the sequence that would be used when you enter an interpreter or call a function or call a C function. So those are actually very tricky pieces of a code. And there, in those cases, actually specific registers are used. So for example, A0, A1 and things of that nature. So they are highly, highly target specific. And another one is called regular expression. So, and WASM, these are WebAssembly ones. So bear in mind that even though I mentioned like these things like compiler, backend, or codegen, and built-in, and all of these have target specific thing, there are actually a lot more files that are target independent. So only the target specific ones are put under the RISC-V 64 directory. So here the takeaway point, 2 points. One is I want you to get a sense of what the assembler interfaces are like, and the middle one, the turbo assembler, the lower one, the assembler, and the upper one, which is the mapping from code generator. So just so that you have a sense of these different kind of lowering, because if you look at this is really progressively lowering from higher to lower, from platform independent to platform specific code. So that's number one. And number two is what I mentioned, that I'm showing you the part that is platform specific, but keep in mind that the amount of code that are platform independent are a lot more than this, which is the good point of a mature layered architecture. Okay, so how do we go about building a backend? So we actually made a few observations here. So the first one is like V8 is a huge code base. It's sophisticated. It's a pretty mature language VM. I think it has at least 10 years, maybe more years of history. And it has gone through several major software architecture refactoring, which are all good things. And as I mentioned, the architecture-specific part is only a small fraction of the entire V8 code base. So the good part is that it minimizes the porting effort. The bad part is that you probably wouldn't be able to fully understand V8 in a short period of time. So development is easy, but debugging would be hard, because when you debug, you actually have to pay attention to the execution flow from the platform independent part to the platform dependent part. So, and the third one is that V8 codegen involves a lot of assembly code, even though we didn't really use inline assembly, but the abstraction or the concept are very, very easy. As I mentioned, even the ignition quote interpreter execution still require code generation. So there is no easy way. So for example, if you have an interpreter, typically when you port to a new backend, you would start with enabling the interpreter, which is basically just enabling the C code. But we don't have that shortcut for V8. And then we also observed that V8 has supported multiple backends. As I mentioned, we are the 8th or 9th ones. And in fact, a lot of, most of them, I'm not sure about x86, but like ARM, MIPS, and TPC, these all share a very similar structure. Sometimes you see comments that are for ARM that are in MIPS. So I do suspect people are like sort of referencing each other's architecture, and which is the approach we're taking as well. And the last one is that V8 provides a rich set of test cases. In fact, you can test both at the JS level and below the JS level. So these, for example, CC tests and unit tests are test cases that are written in C++, but they are able to test specific components inside V8. So for example, I could test individual assembly instructions I'm generating for RISC-V without bringing up the entire V8 VM. So these turn out to be very convenient. And when I say they have a rich set of test cases, it's not just the sheer amount of test cases, but the thoroughness of the test cases. So for example, when it's testing a particular, say, floating point instruction, it defines all kinds of input, testing all the boundary conditions, like maximum number, minimum number, not a number, infinity. And if you do, for example, conversion from integer to a floating point to integer, it would define the floating point to be just the maximum integer and the maximum integer plus 1 and all of that. So it turns out to be very handy of validating the semantics of the instructions or the APIs we're implementing. Okay, so based on these observations, we do see a lot of plus point. So mature architecture layers, so we can only focus on a small part of the code for the porting. But on the other hand, this is just the tip of the iceberg. So when we are debugging, we don't get that lucky. We got a lot of code and we have to figure out why, right? And a lot of test cases is always a plus. But you need to be careful of how you're testing things because debugging is so challenging. It's actually a lot easier if you expose bugs in simpler test cases than if you're debugging a huge JS file with thousands of lines of code. And having multiple backends and similar structure, this is something we can take advantage of. And this is actually the approach we are taking. So these are the observations. And in fact, I think the major key conclusion we made out of this is we realize V8, new backend, the main challenge is not actually the coding, the development of the backend. It's the debugging part of the backend. So that guides our approach of how to go about the new backend. In fact, we deliberately choose to approach that would allow us to debug easier than to code easier. Okay, so now let's go back to the original question of how do we bring V8, how do we add this RISC-V backend to V8? So there are several options. Usually you start with enable the interpreter mode, and then no op, and then full op. But then the interpreter is really not an interpreter here, it's a jitless code generator. So even for enabling the ignition engine, you still have to enable the code gen. So basically you still have to do the same amount of work. Or another approach is to do it as a demo-driven way, so we can get Hello World running, and then after Hello World, we can gradually try out more complex JS code. So this turns out actually Hello World is not that easy because in order to run any JS code, you have to bring up V8, the full V8. And in order to bring up the full V8, you have to compile all the built-in functions. There are thousands of those. So first of all, you need to be able to compile them without any compile time error, which is a step that is in the V8 build process. The built-in functions are pre-built so that they don't have to build it online. And secondly, just invoking a JS, even if, because most of the built-in functions, after you compile them, they may not be actually invoked when you are running a simple test. But still, even for a very simple JS code, you go through a lot of these assembly built-in functions, and then the interpreter bytecode handlers, and so all of those. So it's not as simple, and it's easily thousands of lines of thousands of instructions being executed, and typically people would start with QEMU, and that's the sort of the typical option. And then we took some time to think, like, how do we go about that? As I mentioned, that we realized that debugging is more difficult than coding for developing this backend. So our focus has been, like, how do we go about this so that we can reduce the complexity? And our solution is to define the minimum functioning V8 RISC-V with minimal code changes, don't care about performance in the beginning, reuse as much code as possible. Once we have a functioning baseline, meaning that we pass most of the V8 extensive set of test cases, then we can go back and then refactoring, get rid of the things that we inherited from other backends and focus on improving the code generation and even improving some of the software architectures. So that's the approach we're taking. So our strategy actually also is our roadmap. We started, instead of starting directly from QEMU or real hardware, we started with something called a simulated build. So this might be foreign to a lot of people. So simulated build is a special build of V8. So let's use x86 as the host machine. When we do the simulated build, we'll build V8 as an x86 binary because this V8 is going to run on x86. But we'll specify the targets, code gen target to be RISC-V. So basically, anything that is going through the code generator, the binaries being generated by V8 is going to be RISC-V binary. So how are you going to run this? Like x86, V8 plus generated RISC-V binaries. And this is the simulated build. So because V8 is language VM, so code execution is controlled by V8. So when it encounters a RISC-V binary, it will automatically switch to, in the simulated build, it will switch to this built-in simulator. And in this built-in simulator, it will simulate the registers and instructions. So it will be able to simulate the behavior of what this RISC-V binary is doing. So this is called a simulated build. Of course, this would not be acceptable for someone who is actually wanting to use V8 on a RISC-V board, but actually we can do a lot inside this simulated build. Can fix a lot of bugs, and before we cannot move any further, then we can move onto the QEMU and then onto the real hardware. So the benefit of simulated build, the first benefit actually was just the development environment. So being able to run and debug on x86 is much productive than running and debugging in QEMU on the real hardware. And you can add CI over there, which is very important because we don't want to have any regressions for the subsequent changes. But later on, then we find that there is this built-in trace option for the simulator. So we can actually dump out the RISC-V instructions being executed, and we can print out the register content and the memory address and all of that. So it turns out to be a great debugging tool for us. So that's how we are going from this simulated build to the later one. So the simulated build might be a little surprised for people who are used to just go directly to the QEMU or real hardware. And then on a orthogonal dimension, how do we minimize or maximize code reuse? So what we did is, I don't know if this is what other backend does, but what we did is initially we copy over MIPS64. So this is what we call the fake backend. So we define all the RISC-V macros and then copy over MIPS64. And then we make sure this runs. So basically I have a V8 built for x86. And even though I specify the target as a RISC-64, it's generating MIPS64 binaries and simulating RISC-64 binaries. But I can run all the tests and see which are like 90% of them are passing. So that means that I have identified all the places where things need to happen. And then the second step is actually to replace all the MIPS64 implementation with the RISC-V64. And there in this step, actually, we try to minimize the code changes. So we preserve the macro sampler API from MIPS. Remember the D@U interface I showed before? That carries the legacy from MIPS64. The reason we do that is because turbo assembler APIs are used in many places. And if we preserve the same interface, at least for now, then we don't have to change all the places where those APIs are used. So that actually significantly reduces the number of changes we have to make in the beginning. we even go down the path of preserving the assembly level MIPS. So basically, for some of the assembly codes that are used, we keep those APIs and we implement the semantics using RISC-V instructions. But right now, the version we open source, we actually did a major refactoring before pushing it out. We got rid of all the MIPS assembler API. So all the assembler APIs right now are RISC-V. And right now we're doing another refactoring to rename all the MIPS turbo assembler API interfaces to make it look more aligned with the naming convention of RISC-V. So, and then for RISC-V 64-bit, we'll go through the simulated build, cross-compiled QEMU and real hardware after we're done with that. In fact, I think the next step would be RISC-V 32, and we could copy 64 to 32 and then start to change and morph it so that we only use the 32-bit instructions. And then we can focus on optimization. Of course, these order can change, but optimizations here typically means either optimization for speed or optimization for size. And then we could add other ISA extensions. Right now, we only support the basic instruction sets. The two top priorities are the new ISA extensions. One is the compressed instruction. This is important for the code size. And the second one is the the vector instruction sets. So that's basically our roadmap. Simulated build, cross build, RISC-64, 32 optimization, and ISA extensions. So I mentioned about the simulator. I want to give people a sense of what it is like. So this is, the command is to run a particular test case, a very simple one called load constants. So this is testing load constant implementation. It's a macro assembler API, and you specify the flag as trace sim. So here, this is what we dump. And you can see there is the PC address, the instruction encoding, the disassembled code, the dynamic instruction count. So this particular test runs about 427 instructions, and the value in the target register. If it's a load store instructions, we also get the address. So basically, you have complete information about the execution of the program, and then we use this a lot to basically dump the trace for not too large programs, and then we can search up and down and see if we can find the errors. And we have also developed tools to map from the PC to the built-in functions that are generating or user code that this instruction is corresponds to. And that is very important because the problem with debugging is like, if you have, say, 1,000 instructions there, like, how do you know which V8 function is generating what, right? So with the PC, and then there is another option in V8 where you can print out all the codes, and it has the PC over there. And with the tool, we actually annotate, like, you enter this built-in function, you exit this built-in function. So I actually don't know how one debug if we don't have this trace. So this simulator trace turns out to be really a critical component of enabling us to be able to debug and develop. So the simulator code is simulator-RISC-V 64. And if you want to know more about debugging, actually the wiki is it's a good source of information. So there is a wiki entry called How to Debug V8. And there we'll talk about the tools, about the trace, and about Turbolizer, about how to debug at the JS level, what built-in functions to use to trigger certain actions. So there are a lot more information over there. So what is our current status? So the RISC-V simulated build, now we are passing 15,000 of the standard V8 tests. That's about 91% of all test cases. So is it high or low? So this is actually, sometimes test cases are disabled because they run too long, or it takes too much memory. So this is on par with what MIPS simulated build is able to pass. So right now, actually most of the JS side, most of the issues are cleared. The only ones are related to ASM.js. So so ASM.js is sort of the precursor of WebAssembly. And if you know WebAssembly, it's a static IR. Basically, it's allows one to compile like a C or C++ or Rust programs into a type-specific form and interact seamlessly with JS. So ASM.js, these test cases, even though it's under the MJS unit, like a unit test, it's actually very large. So right now we are debugging a couple of these ASM.js workloads. One of them is called Poplar.js. It's actually an Acrobat rendering engine. And other ones include Lua. So I guess it compiles from Lua interpreter, perhaps, and then SQLite. And all of them seem to hit the same bug. It's a challenging one to debug. So I just want to emphasize that it's very, very important to expose bugs earlier than having to dig a bug out of like thousands of lines of JS codes. And another area that we haven't fully resolved is the WASM tests. So in fact, we have triaged all the WASM failures before we open source, and then after we open source, because we started to pull from V8, the original source, and it turns out they added new test cases, and those test cases, about 80, I think, tens of those, like less than 80 of those are failing. We haven't investigated that, but I do know that the WASM part of V8 is going through a lot of changes. In fact, they have two compilers. One is called the WASM compiler, the other called lift-off compiler. So maybe in the past year or so they have changed, and also WASM standard is evolving. It's still pretty young language. So it could be that just we're using an older version of V8 that does quite work with the new test cases. So that's for the simulated builds. We're pretty confident that we have covered most of the problems in the simulated build. Performance is not good. We didn't look at that yet, but functionality good. Now we're working on enabling and testing V8 RISC-V in this, what we call cross-compiled build, which is basically build V8 as a RISC-V binary and target as a RISC-V binary. And I was really surprised when PLCT team run helloworld.js in QEMU, and it just run. We never really tested it, and it just run. Of course, it's not like everything would run. So right now we have identified failures already in the existing test cases. We start, again, the same principle, start with simple ones. So we started test assembler test cases and macro assembler test cases, and we already found a few failures, and we're currently investigating that. So for people, especially people who are eager to use V8, you can check the latest status on the wiki. So we have this page called testing status, and there you will find the latest information. Okay, so that's where we are. In fact, this is day 4 of our open sourcing. So it's really a new world. What we have done so far is to define a strategy that seems to be sustainable, and we are ready to get more help from the community. So right now we have defined several work groups or maybe work areas. So the one highlighted in yellow are the ones that we need immediate help. So testing and tools. Again, as I mentioned, debugging, that's the most challenging part. And we really want to stress test and expose bugs early and in simpler test cases. And tools, very, very important. The second one is the cross-compiled run enablement. So we have already very promising results in terms of Hello World running out of box. But this is critical because only after we're able to run in QEMU or actual board, we can say we have a functional V8 RISC-V for people who want to use it. And other work groups include upstream preparation. Eventually we want to upstream, perhaps at the end of the summer or in the fall. RISC-V 32-bit support, performance and optimizations, and as I mentioned, other IS extensions, especially C extensions and V extensions. Workload bring up. In fact, we felt if we could have cross-compiled run enabled in QEMU, for example, we could try Node.js. Maybe it would be okay, or maybe there are some other aspect of Node.js that's also target specific but not related to V8. But it would be an interesting workload to bring up. And finally, documentation. So this is also very important for people to understand what we're doing. And I also have the feeling, because when we were working on this, we felt like there's not a very good documentation on the semantics of all the IRs. Some of them you can guess, others it's actually very ambiguous. So for example, what happens when you have overflow? Do you, like for example, if you look at WASM spec, they define precisely what happens when you overflow, you trap, or you round to a particular number. But inside the V8 at different levels, the semantics of a conversion that might overflow, I have to read the MIPS implementation to guess what's the semantic there. And similarly, like the semantics of bytecode, I think I've seen the PLCT team had a session on explaining the bytecode semantics. So maybe as we are contributing this backend back to V8, maybe we can also do more documentation for the V8 IR aspect. I do feel that V8 is a great software architecture, but the documentation side is a little bit light compared to the other infrastructures. So these are for developers. If you're interested in any of the work groups and feel you have something to contribute, you can join our Slack channel. That's where a lot of the transient discussions or questions or status or logistics are happening. If you are just users, you're not compiler person, you just want to use V8, the best way you can help is to follow our instruction to build and then try it on whatever you want to try and file bug report via the GitHub issues. And I also want to say we had a great start. So PLCT team opened open source, I think last weekend, right? And then we open sourced on Wednesday, and on the first day we open source, we already sent very good words about our code base, and then he just immediately decided that it doesn't make sense to have two different code bases. So we joined force right away, and it turns out to be really a win-win because we have been focusing on simulated build. We didn't quite go into QEMU or real hardware, but PLCT team has a lot of experience with that. They have successfully bring up Hello World on QEMU and the real hardware, and they actually have the real hardware. So we already find a lot of places where we can collaborate. For the community operations I mentioned, we welcome community to participate. We are using the pull request model, code review, and all of that. Most of the dev discussions would be captured in issues, but we also have the Slack channel, which can be convenient for just Q&A. And you can find the information on how to join the Slack on the wiki homepage. Okay, so I think I'm almost done. I know we need to save some time for questions. So if as a developer, if you want to get started, how do we get started? I would recommend you start with reading this post called Understanding V8 Backend Architecture. So the link is here, but if you go to the V8 wiki, our V8 wiki, you will find it in the technical document part. So I just put it up today, and it was actually, that was the result of our early study of understanding V8 backend. And I personally found it very helpful to give us a global view of how V8 backends are structured and where the target specific things are. So start from there. I'm still revising it, but I felt it's so important that I just put the raw thing out there. So just ignore all the typos and stuff, but try to grasp the information there. And then you can go to, once you have a higher level understanding, you can go to study the source code and that you just grab everywhere where there is RISC-V 64 directory. There are about maybe 8 or no more than 10 of those. And in particular, I would like you to focus on CodeGen. Under the CodeGen, this is where the assembly API are implemented. This file defines RISC-V instructions. So if you're familiar with the RISC-V instruction set, this file looks very familiar to you. Macro assembler RISC-V 64. That's the D@U example I showed there. So this is actually the most important part when we port, and that requires a lot of attention to details and also understanding exactly what this a particular API is trying to achieve. Sometimes you have to look at other architectures to, or how this API is used to figure out the semantics. This is where I felt like the documentation might help. So that's this one. And then constant RISC-V 64 that defines the constants for like instruction encoding and all of that. And this is shared by other directory as well. So this would give you a good understanding of how the RISC-V machinery is represented. And registers is about the register convention and all of that. And this turns out to be a very tricky part, because if you get the register mapping wrong, oh, it's just such a hell to debug it. And the second important one is the compiler backend, RISC-V 64. So the most important one is, I think it's code generator, RISC-V 64.cc. So this is a part where you lower from machine node IR, which is a turbofan level IR that is machine independent. Even if it's called machine node IR, it's actually independent, to target specific turbo assembler APIs. So the K-arch double 2C, that case statement, that's taken from this particular file. And there's another one called instruction selection. So this is to map some of the targets, the typical machine node IR to these architecture-specific machine node IR called, which starts with K-arch, like the one I showed you. And then built-in RISC-V 64. So this directory contains all the ASM built-in function implementations. These are the hardest to understand because it deals with stack frames and how do you adjust the stack pointer, and we spend a lot of time debugging these ones, but these are very, very important. And then for the simulator support, it's under execution RISC-V 64. It's quite straightforward. So basically you emulate the behavior of each instruction. But here, what special attention needs to be paid on these corner cases, like how do you represent not a number and overflow, and how do you set embedded like floating point CSRs and things of that nature. Yeah, and then for the WebAssembly part, this lift out compiler, you only need to port this part. In fact, the porting we need to do for the WebAssembly path is quite small. It reuses a lot of existing infrastructure. And then the regular expression part. So these are the main part. I think there are a few other directories I didn't include there, but I think the top 4 are the most important ones. So as you can see, it's not, even though V8 is huge, the backend code, once you have a good understanding of how things are going, then the actual code that you want to focus on is not that much. The difficult part is to figure out how to debug it. Okay, so I'm going to add more technical blocks to the wiki in the coming weeks. So 2 in particular. One, I'm going to add a blog on how to add an instruction. Like if there is a new instruction, RISC-V instruction, how do I add a new instruction to the RISC-V backend? What places I need to change and test cases I need to add. And the second one is how to add a new backend, because we are planning the RISC-V 32-bit backend, and I want to write it up so that we have a recipe of sort of following the same recipe of 64-bit, and then just document that. But there are more to come. Okay, so I think that's the main part. And in conclusion, so I think for anyone who is interested in developing a backend for V8 or maybe for other language VM, perhaps for V8, I think for us the main takeaway is a key decision we made is that we realized the complexity or debugging is the key challenge. So when we go about it, we actually take some time to choose how we want to go about it. And I think the fact that we're starting with a simulated build and the fact that we faked from MIPS and try to preserve MIPS interfaces as much as possible to reduce the amount of code changes in the beginning, these 3 decisions are critical to us. Perhaps the last one is we didn't jump directly to Hello World. Instead, we started with CC test and we tried to test things thoroughly in smaller test cases. So I think these 4 decisions are, in the hindsight, are really critical decisions that help us to save a lot of work. Actually, in the hindsight, it's pretty straightforward, but when you are like moving fast and try to get something, a lot of times we may not have the time to think about it. But I think it's very important actually to have a bigger picture and then think about what's the best approach and what's the major challenge and then what's the best approach to address that. So I want to say something about where we are. So we have the basic functionality, but it's not complete because we are still at the simulated build phase. But the fact that we are passing test cases similar to MIPS simulated build, that means our main functionality is there. And now we are, with the help of PLCT team as well as with the RIOS Lab team, we are moving rapidly towards enabling cross-compiled build, which will make our release be really a real release for people who want to try it out, as well as moving on to 32-bit support. So I want to emphasize that there is still a lot of work to be done. So I mentioned all of these things that need to be done. But at the same time, because our way of going about it, I have confidence that we could achieve that if in a short period of time, if we have everyone binding together. And finally, the most important thing, we're inviting the community to join us to build. So far, we didn't talk about performance, right? So in the end, we want to build a high performing and also complete support. This complete support is especially important for RISC-V because RISC-V is an instruction set that is sort of can be pieced together with different subsets of extensions. So there again is a complexity issue. So how do we accommodate to different hardwares that are supporting different subsets of instructions, as well as custom hardwares that have their maybe own design, own extensions, right? So I think I felt the second part can be quite challenging. We haven't given it too much thought yet, but I think it's a high goal to get to there. I think that's my last slide. Yeah, we have 5 minutes, but I can stay longer if people have more questions. But if people need to leave at the top of the hour, I'm fine too. Okay, way back to you. Is there any questions or?
Yeah, there are some questions in the Zoom chatting, which I think you might see it directly.
I haven't seen it yet. Can you say the questions? Because I was okay. Let me see. Oh, chat. Let me see.
Chat.
Oh, how to keep up with the V8 upstream changes. So we form a work group on upstream. We don't know how to. So first of all, we are going to upstream. So once we are into the community, then any subsequent changes to V8, we'll get that because we will be part of the process. But before we are able to upstream, it's really a speed issue. Are we fast enough to get a functioning one merged in? Otherwise, we'll have to chase after that. Actually, I'm not that familiar with the V8 community, so I don't know how fast they are changing. Second question, built-in changes. Can you clarify what do you mean by built-in changes like pointer compression? Wilfred? We could not hear you. Maybe you're on mute.
So maybe we can start the third question. Will Google start?
Sure. So far, we didn't hear Google starting to work on RISC-V backend yet.
And we do see Prama start to
oh, okay, I see here.
From the Android team.
I see. Okay. Yeah, but we did see, actually, today we got several pull requests from someone with the google.com email address. So the the person is very familiar with RISC-V instruction set, so I don't know what's his background of he's working on the V8 or on the RISC-V side. Yeah, but we are, I think the RIOS Lab is in touch with V8 team. And from my sources, I don't think they have a backend yet. And also, if you look at the history of V8 backend, so apart from ARM and x86, which are maintained by Google, for PPC and MIPS, they are all maintained by sort of vendors like IBM or MIPS, or I think right now it's another Chinese company is maintaining MIPS backend. So they seem to be, historically seem to be open to third party maintaining new backends. And that's why we are open sourcing it. So, and we are strictly following the coding standard of the other backends. So we hope that with with what we have, we can draw people into our code base instead of starting their own.
Oh, there's
The
another
support
question.
for, yeah, RISC-V, that's the compressed instruction set, right? So that's part of the plan. So this is in the other IS extension part. And it's also like an optimization. I did hear that for a lot of people, the C compressed instruction set is very important. And we didn't support it in the beginning is because we don't want to introduce complexity, because for the C instruction set, I think the instruction length is 16-bit, and you would have 16-bit length and 32-bit length mixed together. But I think the current backend assumes a single instruction length. There is a single variable doing that. So we don't want to introduce that level of complexity at this moment. But I think after we are able to do the cross build, pass most of the test cases, then we should be able to focus on how to deal with the variable instruction length in the backend.
Yeah, and with the same, the RISC-V stack, we might support it in the future.
What is that?
RISC-V stack, vector extensions.
Right, vector instruction sets. Yeah, so I think I didn't look very closely, but I know the WASM path use a lot of the vector support. So I think we need to get the WASM path cleared, and then we can add the V instruction set. And those I'm not too worried about it, because I think it's probably relatively straightforward, just it's a lot of instructions to add. Yeah, I think C is more challenging just because of the instruction length is violating the implicit assumption of the backend.
Yeah, definitely.
Hi, Peng. I am wondering about the detailed roadmap for the RISC-V 32-bit support, other than the assembler part.
We haven't defined that yet, right? So
yeah,
right. So I think once we find people who are willing to work on that, then we can start that discussion.
Okay,
So,
in your opinion, is it enough to just split up the current implementation from the 64-bit backend?
what do you mean by split up?
Because many of the instruction 32 in RV32 are in some ways a subset of the RV64.
Right.
And which are currently implemented. Yeah,
that's right. Yeah. So this is actually an architecture design. We need to think about how do we maximize reuse if it's possible. One thing I would caution is that if I look at, for example, ARM and MIPS, they do have separate directories.
Yeah.
So, and again, I do know that when we mix 32 and 64-bit together, sometimes you implicitly assume it's 64-bit. So there could be some subtle bugs that you introduce just because two things are mixed together. So I haven't decided yet whether we should split.
Okay.
Actually, my original intention is to split just to follow what MIPS or ARM is doing, 64-bit. and 32-bit complete separate directories. But I think we could, actually Bryce was thinking like, can we share at least some of the code bases, like with a common directory or something like that?
Okay, I'll try it out and further discussing it on Slack, maybe.
Right.
Further discuss.
Okay, for the friends in the Zoom meeting, you can directly ask with your mic or.
That's right. Yeah, that's better actually to directly communicate. Do we have any questions from the Blibli?
Currently, we don't find questions. Maybe they just want to just start to try to clone and download the RISC-V ports.
Right.
And by the way, there are a lot of friends who knows you. Maybe they are your big fans.
Oh, really? Okay. Oh, so sad. I couldn't see the what do you call it? 弹幕, right?
Yeah. I think they know you well, and they although they might not work they might not work in the compiler or virtual machine field, but they might read your papers or your previous works.
Okay. Yeah. So yeah, I guess when I introduced myself, we called FutureWei, but we are really the US branch of Huawei, and due to the political reason, right now we are operating more independently. But before that, I was the head of the programming and compiler lab in Huawei. So in fact, I'm going to do some advertising to the branch of Huawei, and due to the political reason, right now we are operating more independently.
Oops.
I'm replaying, huh? Yeah, so for people who are interested in compiler technology, I think Huawei has a very strong team. It's part of the Central Software Institute.
Yeah, definitely. So thank you very much for being so late tonight.
Oh, that's okay. That's okay. I got hyped up when I'm presenting, so it's okay.
Yeah. Thank you. And we think we might have a better time in the different time zone.
Yep. Next time.
Yeah. Do we have more questions in the Zoom? Okay. Thank you, everyone.
All right. Thanks for joining. Bye.
Yeah. The last schedule is that you can open your video if you want, and we could have a cloud picture.
Okay. I guess I cannot escape. I have to open my. All right. Are the rest of the people so shy?
Yes.
Okay. Nobody's wearing mask, huh?
Inside.
Yeah.
So wait a minute. Okay. Okay, that's 1, 2, 3. I'm not sure I'm taking.
Did you take it or not?
Yeah.
Okay.
Wait a second. 1, 2, 3. Yeah, I think I take. Okay.
Right.
Okay. Thank you, everybody.
Thank you
Goodbye.
very much.